Students, this is Akshay again, your physics teacher. Last lectures we have discussed about some basic concepts of statics and dynamics. Okay, so these concepts we have seen. From these lectures onwards, I'll be eliminating Marathi language from our lectures, and I'll be trying my best to present the lectures in Hindi or most of the times English. Okay, so just bear with that. Now, the next concept we are going to see is viscosity. Okay, so viscosity is the study of real fluids. Okay, till now we have been looking at the ideal fluids. Okay, so the pressure drop is nowhere, the velocities or the flow is streamlined, nothing is happening, or the streamlines are parallel to each other, or the velocity profile we were seeing, it was like this. Okay, so from here onwards we'll be looking, or we'll be considering the fluid as real. Okay, so what exactly real means? See, if I take an example, let's say there is a block on the ground. Okay, and it has a mass m. Okay, so mass m is, let's say it is 1 kilogram. Now you want to pull this mass with certain force, but the ground is offering some backward backward driving force, or let's say opposing force, that we call as friction. So there is a particular frictional limit. uh, More than that, if you apply your applied force, if you apply, it will start to move. But let's say in certain case, if I place some another mass on it, so this is m1, this is m2, so the combined mass is greater than the previous, so this limit will increase. So in the 11th you might have seen that this friction, it depends on the normal reaction. Okay, the normal reaction in this case depends on the mass. Okay, or the weight. Simply the same thing happens in case of fluid. Let's say here I'm showing some layers of the fluid. This is the layer 1, this is second layer, this is third layer, this is fourth, this is fifth, and this is sixth. Okay, so let's say at the topmost level, uh, just cancel it out, dv. Let's understand from very basic. Let's say at the top of the surface, the fluid has a velocity v. It is moving with the speed v. Now, for the next bottom layer, that is fifth layer, the whole mass of this layer will be offering some normal reaction at the surface. So now if I consider it as a real fluid, this layer will apply a frictional force on the upper layer in the backward direction. Okay, so what will happen? Or similarly, uh, if I consider this fourth layer, these two layers will now apply some normal reaction on this layer, and for their movement, this fourth layer will apply some opposing friction force, so that the velocity goes on decreasing as we move to the bottommost layer. So now if say here the velocity is v, now it will be v minus dv. Let's say next time it becomes 2 dv. Okay, so simply just don't consider these values. I'm just saying that the velocity is decreasing. Okay, so what happens, due to their individual weights at the bottommost layer, it has to bear the whole weight of this flow or the layers, so it will have a minimum velocity, and and the topmost layer, it will have a maximum velocity. Okay, so this is exactly happening in the real fluid. Till now we have been seeing at the ideal fluid, so there were no frictional forces, nothing. That's why these streamlines of, or let's say these were like this, and this velocity profile was like this. Okay, so from here onwards we are talking about what? We are talking about the real fluid, where the intermolecular friction, or let's say interlayer friction, comes into picture, and that friction or that force is called as viscous force. Okay, so what is the exactly meaning of viscosity? It is the viscosity is the property of the fluid by which or the by virtue of which it opposes the relative motion between adjacent layers. Okay, so this is the exactly concept we are going to see from here onwards. So now what exactly is happening, just consider two layers. Okay, just consider two layers like this, and this is first layer, this is the bottommost layer. Let's say it is moving with a speed v, the bottom layer is moving with speed v, and the uppermost layer or the upper layer will be moving with some extra speed. Okay, so there is a relative motion between these two layers. So I hatch these layers to differentiate their representation. Let's say the upper layer is moving with some extra velocity than the lower one, so it has a greater speed comparing to the bottom layer. So it will, there will be some relative motion, and the force that will oppose the relative motion in case of the fluids is called as viscous fluid, viscous force. In case of solids, the force that opposes the relative motion between the two objects or some, it is called as simply friction force. But in case of fluids, it is called as viscous force. Okay, so experimentally, so this is empirical, or let's say it is observed that this viscous force, I denote it by F suffix V. The viscous force depends on the area. Okay, unlike that of the frictional force in the solids, which does not depend on the area, here the viscous force depends on the area of these layers. Okay, so let's say if I take a section, and if I take this section, so this is the uppermost layer I'm showing by hatching, this is the bottommost layer. So this whole area, and I'm talking about this whole area, it depends on the viscous force depends on that area, because that much molecular adhesion will be there, or normal reactions will be there. Okay, also the viscous force depends on, it is called as velocity gradient. Okay, so what is velocity gradient? Velocity gradient means here there are not only two layers, there are many layers in the fluid. I'm just showing some layers. So what exactly is happening, as you move upwards, some incremental velocity or the velocity is it is increasing. Okay, so very micro change is there. So with the increase in the height, with increasing the height, the velocity is increasing. So I can say the velocity has some gradient in upward direction, and that is called as dv by dy. So let's say यहाँ पे देखिए एक्चुअली जो मीनिंग है इसका, कि अगर इंक्रीमेंटल हाइट हो रही है, मान लो इसमें मैंने छोटा सा एलिमेंट ले लिया dy वाला, तो इसमें अगर यहाँ पे वेलोसिटी v होगी तो यहाँ पे कितनी होगी v प्लस dv. So what is the change in velocity between those two layers? It is dv. So it is called as velocity gradient. Okay, so combining them, the viscous force depends on area into dv by dy. Okay, and the last expression for this viscous force, if you remove this proportionality sign, there will be some constant. Now I draw here a constant like this, it is called as eta. You will pronounce it like eta, a into dv by dy. Okay, so this is the final expression. This is the final expression for the viscous force between or among the layers of fluids. Okay, and here this term dv by dy, it is called as velocity gradient. Okay, so you will learn about this velocity gradient more accurately or more precisely when you will be in second or third year of engineering. So by now, also in JEE, the questions they have been asking are not that much difficult about this equation, and viscosity is not that much important for JEE uh, in case of in terms of difficulty, because there are two or three formula, and most of the questions asked for JEE are based on those formula memory based. Okay, so you just mug up this formula and you try to solve it. Okay, so you can crack this topic, viscosity. Okay, now we'll have a note about this viscosity. Some points we'll be noting. The first point, or let's say, it depends on the nature of fluid. Okay, viscosity has nothing to do with other dimensions or nothing. Okay, I'm talking about viscosity. Viscosity means the formula we derived, like F is equal to eta A dv by dy. I forgot to tell you this meaning of this eta. It is called as coefficient of viscosity. Coefficient of viscosity. Okay, so now we are talking about this coefficient of viscosity. So the first point here is that it depends only on the nature of fluid. Okay, so okay, and it is independent of area. Now I know most of you are confused here. See, the viscous force depends on the area, not this constant. This constant is independent. Similarly, if I relate it back to your ninth class concept, that the gravitational force is equal to G m1 m2 upon r square. Let's say, for example, here the tricky question was asked in one of the CBSE exams was G is equal to Fg into r square, so m1 m2. And the options were given like depends, G is inversely proportional to m1 m2, G is directly proportional to square of the radius. No, this is wrong, because G is called a universal gravitational constant. It is, by its definition, it is a constant. Okay, so here also the eta is a constant, so it is independent of everything. It will only depend on the fluid you are choosing. Okay, so for water it will be different, for air it will be different. It will not depend on any of these parameters. No, it is constant. So the force is dependent on this area and everything. Okay, and obviously the eta is independent of area and the velocity gradient. Okay, it will only depend on the nature of the fluid. Its dimensions are, now these dimensions most of the times, yes, in any concept they will ask you about finding out the dimensions, so you can easily find out the dimensions here. Let's say how to do that. Let's say F is equal to eta A dv by dy. Okay, now we need to find the dimensions or the unit of this eta. So I can write eta is equal to F upon A into dy by dv. It is no gradient. Okay, and just I have reversed the order, so don't consider otherwise. This F upon A, or I can say this is Newton per meter square, and here dy means simply the length is meter, and this velocity is meters per second. So meter gets cancelled, the second comes upwards, so this is Newton is kg meter per second square upon this meter square into this second. Okay, so this meter and one power will get vanished, so s this, so this is kg kg per meter per second. Okay, so the dimensions would be like this: m, the kg comes only once; l, the length, it is also coming once but it is in denominator, so -1, and t, that is -1. So simply you can derive in this way. I don't think they will ask this in board or anywhere. Okay, so this is clear now. Next, this is also clear up to here. Okay, now the most important thing, the SI unit of the coefficient of viscosity is Poiseuille. Okay, it is pronounced as Poiseuille and it is given as PL. Okay, not PI, it is PL. Okay, while CGS, most of the times we will be using this CGS unit. Okay, and it is called as poise. Okay, simply it is given as P. Okay, forget about this. This is here it is dyne second per square. I don't think, just don't consider this. Just keep in this mind the SI unit is Poiseuille PL and the CGS unit is P. Okay, so this is where you need to concentrate now. Okay, so the conversion factor they have given, it is 1 PL is equal to 10 poise. Okay, so this is most of the times they will be giving this coefficient of viscosity in terms of in this CGS unit, and other everything will be given, or density, let's say area, everything will be given in SI unit. So you need to convert this into SI. Okay, though it is used most of the times in CGS unit, the coefficient of viscosity, you have to convert it to SI, and for that the conversion factor is like this, means in 1 PL 10 poises we are getting. Okay, so means this is higher than this is not higher than this. Okay, in 1 it is 1 fighting against 10. Okay, like 1 rupee is equal to 10 paisa, like this. Okay, this is higher than this, like this. Why I'm telling you this, because most of the students they get confused while solving this problem. This is this is very simple, but simple things are more, most of the times they are complex. Okay, so the next important thing we are seeing here, that the viscosity of liquids is much greater than that of the gases. Obviously, because the intermolecular forces between the liquids are much higher than those of the gases. That's why this relation holds true. Okay, now I'm going to tell you some extra points. Those are not listed here, just consider them. That for liquids, okay, for liquids, as the density increases, the viscosity or the coefficient of viscosity also increases. Like for example, if you take honey, okay, if you compare between water and honey, which is more viscous? Obviously honey, because its density is higher. Now if I talk about gases, okay, if I talk about gases, it is little yes, it is different. Okay, if the density increases, the coefficient of viscosity or the viscosity decreases. Why? Because in gases, if you see the molecules, the gaseous molecules, if you see, if you are increasing the density, means you are adding more number of molecules in the same space, isn't it? So the collisions will increase, and to dissipate that energy, it will flow. Okay, the gas will flow somehow. If it is not enclosed, it will start to flow, And if it will start to flow, actually the viscosity will decrease. Okay, just the flowing ability is called as sometimes viscosity. So if it is flowing due to addition of more molecules, or due to increase in density, if it is flowing, it means that its viscosity is decreasing. Okay, so these are two points I wanted to add to this notes, so you just write them down. Okay, now it's time to solve some numericals based on that equation we called as the equation of viscous force. It was given like this. Okay, and just kindly concentrate while solving, or while I'm solving these examples, because the approach is more important. Okay, you will solve it within 2 minutes or 10 minutes. Okay, so if you choose the correct approach, you will solve in 1 minute also. So the equation is simple like this: Fv, or the viscous force, is given as coefficient of viscosity times area times velocity gradient. So here let's say the velocity of water in a river at the surface is 18 kilometer per hour. Means, let's say if I take a section of that river and this is the ground. Okay, so I'm taking a section and this surface is moving with 18 kmph. Okay, now we know that we need to convert this afterwards, so just keep this like this. Okay, now if they have given the coefficient of viscosity like 10 raised to minus 3 Pascal, so the velocity obviously it is decreasing. Okay, and most of the times they don't give the velocity at the bottommost layer, but we will consider at negligible, like it is 0. Okay, so if I take this whole height, means the river is given as it is 5 meters deep. It is not possible, rivers are not that much deep. So 5 meters deep, and in 5 meters the velocity has increased from 0 to 18, or inversely we can say it has decreased from 18 to 0. Why? Because of the viscosity. So here from this given condition only we can write the velocity gradient like this. So the change in velocity, it is 18 kmph, and change in distance means the distance between two points, the bottommost and the uppermost, that is what the distance we are taking here. In this distance, in this gradient, the velocity has increased or decreased like this. So most of the times it is actually negative, the velocity gradient. If you are choosing this positive side downwards, if you are choosing positive, the velocity is decreasing, means this will be negative. If you choose the upwards as positive, it will velocity will gradient will be positive, but it is not that matters. Now here we will see the distance is 5 meters. Okay, now we'll convert this 18 kmph in SI units, because here it is meters. So we know that magic number to convert kmph into meters per second, that is 5 by 18. We know that. So it will be 18 gets cancelled, so it is 5 meters per second, and this velocity gradient here we are getting as 5 meters per second divided by 5 meters. Now it is 1. Okay, I will not write its units because it will get much complex or intricate, so I will keep this as it is. Okay, so here now eta they have given in Poiseuille, so it is itself a SI unit, so no need to convert it. So this will be 10 raised to minus 3 into area into this is 1. Okay, dv by dy we have obtained at 1. Okay, isn't it? And this will be viscous force. So now what to do? Because area is not given, nothing. So they have asked about the shearing stress. Okay, shearing stress. If you don't know about what is shearing stress, it is the stress that the liquid or the fluid is unable to apply. The ideal fluid is unable to apply, and it keeps moving. But here, due to the shear stress, the velocity is decreased to nearly zero. So some shear stress is being applied here, and the shear stress is given as tau. It is called as tau, not tau. Okay, it is called as tau. It is given as viscous force upon area. So here, if I take this area across this boundary, it will become Fv divided by A is equal to 10 raised to minus 3. Okay, so this Fv upon V, it is tau, the shear stress the liquid is applying between its two layers or opposing the flow. It will be 10 raised to minus 3, and the stress, it has a unit as Newton per meter square or simply Pascal. So it is Pascal, or you can say tau is equal to 1 millipascal. Okay, milli means 10 raised to minus 3. So this is the answer to this question. I'm not much concerned about this correctness of this answer or nothing. So if you are solving, don't look at the correct numerical value you're getting. You just make sure that your approach is correct. So what velocity gradient, how you are obtaining this? So you should obtain like this. Okay, from surface to the ground, it has decreased from 18 to 0. Okay, so by traveling 5 meters downwards, if I'm decreasing my velocity from 5 meters per second to 0, there has to be some velocity gradient. So how much distance is traveled 5 meter, and how much velocity is decreased 5 meters per second? So this will be the velocity gradient which you are going to use in this expression. Now if you are confused about the area is not given but in the equation the area is there, so they are indirectly asking about the shear stress, which is itself Fv divided by A. Okay, so these two concepts you need to note down right now, so you will be able to solve them.